Noise in measurement systems, film 3, and this is about coupled noise. And of course this is a problem in all kinds of systems, not only in measurement systems, for example audio systems, and also in communication systems. In this example here we have a low frequency signal here, and it's sent into the red conductor there, and we have a higher frequency signal which is sent into the blue conductor. For some reason the signal some part of the signal transfers from the blue carrier over to the red one, and then they mix together, and the result is as seen in the figure there. And the same goes with the red signal here. The low frequency passes over to the blue conductor, and resulting in a mix of the two. Of course the carriers aren't red and blue necessarily, just for the example. But what you see here is that the greatest portion of the signal here is still the old signal, but you have noise on top of it, which comes from the other conductor. And same here. Still, most of the signal is the high frequency signal, but you have some low frequency signal that has been transferred over to the other conductor. So it's also called Crosstalk or XT, because earlier in analog telephones, sometimes when you had a phone call you could actually hear the neighboring phone call on the same line, and that was due to so-called crosstalk. Of course it's undesired, we don't want that kind of noise, and also it's so-called self-generated, that it's generated by the equipment itself. And there are basically four reasons for this noise to occur, and the first one is so-called impedance coupling. And that is a problem when you have like this, you have two senders here. Those could be, for example, two different sensors sending their information on two different transmission lines, but they have one common return path. So the current from one of the sensors would go like this into the load and on the common return path, and the other one would go down this load but follow the same return path here. What this figure also illustrates is that on every conductor you have so-called line impedance. There is some resistance in the line itself, in the copper of a copper cable, for example. Now, if you have a resistance and you have a current, there will be a voltage drop across those resistors there, or across the line impedance. So there will be a voltage there. So sensor number 1 will generate 1 voltage there coming from sensor 1, and there will also be a voltage from sensor 2. So indeed you could measure that voltage down here on both loads compared to the ground over there. So the lower part of the load will have a varying voltage which is dependent on both the sources. That of course will influence when you try to measure this voltage from top to bottom over the load. Well, it's just like if you're trying to measure the height of say for example a vase here. A wine glass or whatever, you're trying to measure the height of it, but the bottom of the measure will not stand still. Well, of course that will influence what kind of height you measure on the wine glass when the bottom of the measure won't stand still. The same goes here. So for that reason the signal from sensor 1 will couple over to load number 2, and the signal for sensor number 2 will couple over to load number 1. Of course, the main signal in load number 1 will come from source number 1, and the main signal in load number 2 will come from source number 2, but some of the signal will transfer from one one transmission line to the other. And thus we have so-called impedance coupling, which comes from the fact that we have one common return path, and this return path has a line impedance. To avoid it, the best thing to do would actually be to not have a common return path. So break the line there, make your own return path for the second load, and they have each one return path each. And that is very common in, for example, internet cabling, where you have so-called twisted pair cabling, one pair for each source. Also, we have something called capacitive coupling. You haven't heard about capacitors yet in MAS 130, but the capacitors, they tend to let through high frequency signals go through them. In order to make a capacitor, you need three things. First of all, you need two areas with conductive material, one area here and one area there. Second thing you need is that you need a gap between them, distance. And the third thing you need is that you need to fill that gap with something that could carry an electrical field. But even vacuum works for that third element that is required to build a capacitor. Vacuum works, plastic works, but you cannot have a conductive material in between them. So a non-conductive material between them in that gap will make a capacitor. And capacitors, they let through high frequency signals. Now, if you have two conductors, two straightforward conductors, wires, there, you have everything you need to build a capacitor. You have area, because two round conductors close to each other, they share common area, close to each other. You have gap between them, and you have a non-conductive material between the two. So there, if you have two conductors close to each other, you have a capacitor which will let through high frequency currents and voltages. Now, of course, that will give crosstalk. So what can you do to avoid that? Well, you can indeed separate the two very much. If I have one conductor here and the other one down here, the gap would be too large for an electrical field to form. Or you can actually, if I have one conductor there and then I have a shield around it with, for example, foil, and I ground that shield, well, then the electrical field from one conductor cannot jump over to another conductor, because the electrical field here will go straight to the ground signal instead. So that's why you have shielding around some pairs in transmission lines. The third problem comes from inductive coupling, and that's where you have inductors. And that comes from the fact around every current carrying conductor there is a magnetic field. And if I vary the current like that, back and forth, well, then I have a varying magnetic field. And also, if you have a varying magnetic field around or close to a conductor, that will generate a current. So this goes back to Maxwell's equations. So the thing is that if you have one conductor here with a varying current, that will generate a varying magnetic field. which will in turn transfer over to the conductor close by and generate current in that conductor. So again, we have a problem with coupling. The workaround here would be actually to twist the conductors like this. If I twist the conductor, and I think that if I have a current going through here via a load and then back again, the current goes back again on the other side. So let's just draw the current for the first to the load and then back from the load like that. This will generate a magnetic field in that direction, and this will generate a magnetic field in that direction. Again, in this direction and in this direction. In this direction and in this direction. In this direction and in this direction. Note how the two here add up to form a magnetic field that goes into the board. Here the two add up to a magnetic field that goes out of the board. So cross there, dot here. Cross here, signaling a magnetic field going into the board, and dot here, signaling a magnetic field going out of the board. So for every turn, you have opposing magnetic fields. So all in all, they zero out each other. So that's why I had twisted pair cables. Finally, radio frequency or high frequency electromagnetic waves may actually form radio waves. So you have actually a conductor being a small sending antenna, and the other conductor here being a small receiving antenna. And you can avoid that again by shielding, but then you tend to shield the entire cable, not the individual conducting pairs.